One source is water. Release its heat energy when put to work in an atomic reactor. Atomic fuel is usually uranium fabricated in a tough ceramic form that will withstand very high temperatures. Small pellets of fuel are loaded and sealed in metal rods. In a vessel forged from thick steel, the fuel will do its work. About 100 fuel assemblies containing 60 to 70 tons of uranium pellets make up the fuel core of a large power reactor. The fuel will generate heat through the process of nuclear fission. These rods soak up the moving neutrons much the way a blotter soaks up ink. The control rods are moved up and down in the fuel core to increase or decrease the rate of fission and heat generation. The reactor operator can plunge the control rods all the way into the core to shut off the reactor at once. Sensitive instruments also cause the shutdown automatically if the reactor is not operating as it should. To carry a fuel coolant always circulates in a closed system, and after giving up its heat, it returns to the reactor to pick up some more. Water from a river or other nearby source is pumped in and out of the plant to cool the turbine system. This water never comes in contact with the reactor. As each fuel atom splits, fission products, minute ashes, are formed. They remain locked within the fuel. About once a year, used fuel assemblies are removed from the reactor. They are stored underwater because they are very radioactive due to the fission products inside. To allow time for some of the radioactivity to subside, they remain here for several months. The water blocks the radiation and cools the assemblies. A used fuel assembly is valuable because it contains a good deal of unused fuel material. Therefore, after the aging period, it is transferred to a container, lifted from the storage pool, and shipped to a chemical plant for reprocessing. During reprocessing, the radioactive fission products will be separated and stored for safekeeping. Thus, almost all, in fact, more than 99.99% of the radioactive matter that was formed in the fuel either loses its radioactivity by natural aging or is removed from the power plant. Most of what's left, together with other relatively small amounts of radioactive material, form safety regulations. These regulations also require regular collection of air and water samples. This air filter sample, along with others, will be precisely analyzed in the laboratory and will provide continuous information of the plant's environment. Atomic power reactors are not potential atomic bombs. The dilute nature of the fuel and basic reactor principles and design make an atomic explosion an impossibility. Safety is strictly a matter of keeping the radioactive material confined. Under normal conditions, this material remains tightly locked within the fuel. Only if a fuel assembly were to overheat to the melting point could a significant amount of fission products escape from the fuel. They would then be confronted with a succession of barriers. Only if a mechanical failure occurred could this material then get out of the reactor system. Even if this highly improbable sequence of events occurred, further barriers and safeguards act to isolate the fission products. Many many safeguards are provided to prevent these things from ever happening. For example, the fuel material used has a remarkable ability to seal, which acts as a barrier against fission product escape. In addition, the reactor is so designed that its natural tendency is to slow down if fuel temperature increases. Also, many of the reactor's automatic safety devices are installed in duplicate and triplicate and are designed to shut down the reactor automatically if the device fails. But the designers don't stop there. Additional safeguards are provided whose sole purpose is to limit the consequences of an accident in the unlikely event one should ever occur. Safeguards are designed to enclose and isolate radioactive material that might get out of the reactor system, thus preventing harmful amounts from escaping from the plant. For example, plants include a sealed vapor containment system, which may take the form of a steel and concrete sphere. All of this is like designing an unsinkable ship and then wrapping a life preserver around it. Plans for an atomic power plant begin with careful study by the utility company. When the utility has decided to build an atomic power plant, it must first apply to the U.S. Atomic Energy Commission for a construction permit. The AEC announces the application, makes it available for inspection by any member of the public. State and local officials are also provided copies. Volumes of details, safety features, and all other matters, the entire correspondence between the AEC and the utility, all become part of the public record. There are no secrets. Anyone with questions may study the proposed project long before construction begins. By law, the plant can be built only after a favorable ruling by the AEC. Before this, the Commission must assure itself that both plant design and proposed location meet the test of safety. A separate regulatory staff studies the application thoroughly, checking calculations, examining equipment and plant designs, verifying data. The regulatory staff becomes as familiar with the project as the designers. Another group, the Advisory Committee on Reactor Safeguards, makes a parallel review of the application. This committee, established by law, is made up of specialists drawn from universities and industry. Giving the AEC an independent evaluation of safety matters is their particular responsibility. Their views and those of the AEC's regulatory staff are added to the public record, available to all. Now comes another important step, a public hearing in the vicinity of the proposed plant. Several groups take part. The utility representatives, the AEC licensing board, made up of 2 technical specialists and a lawyer,
What are the differences? Yes, I wonder
representatives of the AEC regulatory staff, state and local officials, and members of the public.
Of waste material from the plant, which I assume is to be done by truck.
The AEC licensing board conducts the hearing. The utility representatives and the AEC regulatory staff members give testimony, and the views of the community are heard. The hearing provides a review of all project features and serves to acquaint local citizens with project details. Following the hearing and after further detailed study of the record, the board, if it is satisfied that the project fully meets AEC requirements, recommends that a construction permit be issued. Their recommendation is then reviewed by the Atomic Energy Commissioners. What lies ahead? Three years of construction. The plant begins to take shape. At its heart, a foundation of rock, steel, and concrete. Here, the reactor vessel will be placed. Continued inspection by the utility and AEC. Through season after season, the project grows. Miles of steel tubing, tons of concrete, endless skills transforming blueprints into reality. The steel and concrete housing for the reactor nears completion. Of precision. Checking and rechecking. 3 years of workmanship and quality control. Dependability. While construction and manufacturing are nearing completion, plant operation teams are trained. The men who will run the reactor must obtain a special AEC license. The plant is now staffed, ready for operation after years of preparation. The first shipment of atomic fuel begins its journey to the reactor. The utility has already applied for an operating license. Now that the plant is built, the AEC review can include all details and procedures as they exist, not just in plan, but in fact. The review is completed, the license approved. Beyond this, AEC inspections will continue for the life of the plant. Final pre-operational tests are performed. The fuel assemblies are given a final check. Then loading begins. The assemblies are lowered underwater, there to be guided into final position. Everything is in place. The sealed reactor is started and goes through a period of careful, low-power tests. Then the day comes. Quietly, without fanfare, the plant goes on the line. The new facility joins the growing number of atomic power plants supplying electricity across the nation. Atomic power is at work today. It's future assured. The resources are vast. The technology expanding. Yes, we live by electricity and need more of it. The kind of energy that gives its name to the atomic era now is harnessed to our lives.